Hello, and thank you for stopping by on this abstract video. I will be introducing really shortly my paper on robust modeling of GNSS orbit and clock error dynamics. So first, a small introduction and background. It is very well known that inertial and GNSS have very complementary errors. And so combining them using, for instance, a Kalman filter can be very helpful in limiting the drift of the inertial positioning errors, but also on the GNSS side of things, help provide continuity through urban canyons and robustness against the jamming and spoofing attacks. But this GNSS and INS integration relies on filtering over time. Now, in another application, we've also seen that exploiting satellite motion in ARAIM can help reduce protection level and provide superior positioning performance. And so this could potentially also help extend the scope of ARAIM to other applications such as rail, harbor, or Arctic operations. But these two applications require a faithful modeling of stochastic errors, including their time correlation. And now on top of that, we are interested in safety critical applications. And so to ensure the integrity of the navigation solution, we need to have error models that will be upper bounding of the actual errors. Now in prior work, upper bounds have been derived on the variances of orbit and clock errors for both GPS and Galileo satellites. But these errors were not sufficient since they were snapshot error models. And so they were not good enough for time-sequential implementations. And so to ensure that we have both a time-correlated and an upper bounding error models, in this work, we will be using the power spectral density bounding method. And so we are in particular interested in orbit and clock errors in this paper. So how do we generate those orbit and clock errors? Well, we use a truth data from the international GNSS stations, to which we apply a few modifications to make it match to our archived ephemeris, which is what the receiver will see. And so we make the difference between those two data sets and obtain our orbit and clock errors in the radial, along, and cross track. And so once we have those errors, we can separate them by clock type, satellite clock type, and then convert them to the PSD domain and finally upper bound them. In this case, we upper bounded them with the first order Gauss Markov process. So here you have in the upper plot, the GPS result, and the lower plot, the Galileo results. Now, if we look at the table, which represent the parameters, the bounding parameters, we can see that the rubidium clocks for both the GPS and the Galileo have lower errors. And so separating the errors by clock type could prove to be useful. Thank you for watching. If you're interested in the full paper, you can access it via this website. And if you have any question, you can contact me at this email address.